It's great to be here this morning at Framework, my first time here, and was really inspired yesterday by the discussion about the Framework ethos, and I particularly liked the term that was being used, the pixel people. Um, and that really led me to thinking about where Brompton fits into this. And my sort of, I like to think of our sort of internal ethos as really, we are the people to whom you entrust your very carefully crafted pixels that you spent a lot of time on and maybe been up all night creating. You give them over to us to display on a screen, and our ethos is to try and get those pixels the best they can possibly be, to display them as truthfully, and to give you all the tools to create the best possible pixels. So I'm going to talk a bit about the future of LED systems today. We're all pretty familiar with the LED stages that we're on, but where are they going to go? So to start with, a little bit about Brompton. Brompton's background, and indeed my background, is, like many people here I've been hearing, in live events. Our team that founded Brompton started our lives really in lighting control, and so we had a really key understanding of how events work, how you get a show done. Our system is the brains behind these screens, so we take your video signal and we derive those control signals for the LEDs. Starting our live events, cameras were really important from the very start. Our system's been designed from the ground up to work with cameras. And we spent a lot of time developing the industry-leading features and color system, really focused on those live events, but always with cameras in mind, including our unique dynamic calibration. And this made Brompton the really ideal fit for virtual production as that technology started to emerge. For me, my background is in live events, but I also had the privilege to work in feature film visual effects for a few years. So when this technology came together, it was amazing for me to bring together those two interests of mine. And really for Brompton, we're interested in any area of display where quality is the focus. We're constantly focusing on quality and how we can improve systems. In the virtual production space, where we've been involved almost since the very beginning of these LED screens, we've kind of got the basics done. It kind of works. And what we've been really focusing on for the past few years is building the key tools that people need to bridge the gap between different technologies and people with different backgrounds. And we've built some fantastic tools to solve key problems like having the LED processing systems speak the same language as DPs. Things like shutter angle, a concept that most LED systems didn't understand. You can now talk to Brompton natively about shutter angles and we understand what that means. We've also been building tools to connect the DIT and the gaffer to the LED system so they can use the systems that they're familiar with a language that DPs are familiar with, to control this new technology and giving them all that creative power that comes from that. So what's next? We've kind of got the basics down. Where are we going to go? What can we improve? And I'm sort of thinking about this from the perspective of, how can we improve quality, efficiency, and give people better workflows? So to enable all this, we found we really need a new platform. A huge amount of the power of a Brompton system lives in the tiles themselves. Only the tile really knows about the properties of all its pixels, and it's not really practical to move that data around into a central location. So we do a lot of the work there. And to drive developments that we wanted to do, we needed a new platform. It's not something we do lightly at Brompton. Our R2 card has been around for 9 years. It's still the most powerful receiver card on the market, and it continues to be, in many, many quality metrics, simply the best product. We've been continuously updating it over the years. When we started, we didn't have HDR and dynamic calibration. We added that. In the past few years, we've added shutter sync to enable you to match the LED refresh very precisely to the shutter. And even in this past year, we've added extended bit depth, massively increasing the dynamic range available on tiles. And these updates have all come to existing platforms, so people investing in Brompton have got a lot of value out of that. But we needed more power, we need more to extend. And that's why we launched this year our new receiver card, the G1. This is a next-gen receiver card for those next-gen panels, pushing on in towards new technologies, new ideas that people haven't even come up with yet. To give you a bit of a flavor of what the G1 is, it's about 20 times more powerful than our R2 receiver card, which was already the most powerful on the market. It enables larger, finer panels, up to 1 million pixels on a single receiver card, and we can drive them faster, up to 1,000 frames per second. It's worth noting that the panels that this card can drive don't exist yet. They're not on the market, so we are really looking at the future and what could be possible. The panel takes 10 gig fiber straight to it. And this really simplifies distribution, cabling. We can take 5.25 million pixels down one cable at 60 frames a second. So it's a really powerful platform. And to give you an idea of what that power really translates to, this is a fantastic audience. I know you guys will actually get this. That is a 720p display in a single panel driven by a single receiver card. So it's crazy powerful. It's a platform for the future. So what have we built on top of this? Well, today I'm really going to focus on one technology that we've been developing, which is actually a little bit different, and it's called TrueLight. So to explain why TrueLight's important, we want to, and this is very much driven by virtual production, we need to just consider what the LED volume in a ICVFX workflow is doing. It's a background. It forms the background of the camera, replacing that green screen, giving us our final shot in camera. It's a source of reflections, and it's a source of lighting as well, particularly diffuse environmental light. And this is where we run into one of the problems with displays at the moment. So all the displays we're familiar with, they work using RGB. They have a red, green, and a blue component to each pixel. And the reason why they do this is really simple, right? That's how we see. It's a very efficient way to produce a display. You want to excite each of the eye's 3 receptors for the 3 different colors. So by using red, green, and blue, we can produce any color within a gamut. It's a very efficient mechanism. And that is ubiquitous in our industry, right? All our cameras see in RGB, we all work in RGB, in post, when we're moving footage around, and our displays are RGB. And that means, what we like to say at Brompton, that there's one right answer. So essentially, given an RGB triplet, when we input that into our display, there is a correct answer to what that pixel is meant to do. And that is the correct answer that we at Brompton are always trying to find. But that isn't really how light works. It's a bit more subtle than that. So these 2 spectral distributions are trying to represent the same color. So using an RGB display, we end up with this very peaky spectrum. We've got our red, green, and blue components, and there's some areas of the spectrum that aren't really covered. Whereas a real daylight spectra that looks the same color when it illuminates, say, a white object might look like this. So what does the difference between these spectra actually mean? Well, that corresponds to the term color rendering. So color rendering is the ability of a light source to illuminate objects faithfully in the way we'd expect. And because of this spiky spectral output, these RGB sources have very poor color rendering. They don't produce lots of colors under illumination very accurately. We can do a few things with this. We can use broader spectral output, but that comes with some trade-offs. It reduces our color gamut and our ability to reproduce these more saturated colors. So at Brompton, we've been working on a solution which we call TrueLight. And TrueLight's all about adding an extra emitter to each pixel. But in developing TrueLight, we wanted it to be a zero-compromise solution. We didn't want to take any steps back in terms of quality or functionality. So TrueLight is a fully spectrally aware calibration system built on top of our existing dynamic calibration that enables that extra emitter to improve color rendering. It's a full per pixel calibration system, 0 compromises. I'm going to play a short clip, and then we'll dive into what TrueLight really looks like. Okay, so that was a little intro into TrueLight, a bit of an overview of the technology. Let's go into a bit more detail about what's going on here. So these are some comparison images that we've generated based on this technology. And it's worth noting these don't use any conventional lighting. That's not to say that conventional lighting won't be used with this technology, but everything you're seeing in these images is all illumination from RGBW panels using this TrueLight technology. We'll cover in a second exactly what we mean by RGBW, but for the purposes of this demonstration, let's just look at what the color rendering and the quality is like. So this is our model illuminated under this TrueLight technology light. And this is what it looks like under RGB. So this is what you're getting in every volume today. If I flip back and forth, you can see that all our red tones are massively oversaturated and hyped, and we've got a really quite nasty red cast in the skin. If we look at a split screen, we can really see this effect quite markedly. So once you've seen this, and I've had this experience myself, when you walk into an LED volume from now on, you will not be able to not see it. There's this horrible red cast. You walk into a volume, you've got this lovely, mountain scene with a beautiful blue sky. It should be a really nice cold illumination. You look at everybody and they're all red. Where's this red coming from? It just looks completely wrong. On darker skin tones, the effect is a bit more subtle, but it's just as real. And in this clip, we can also see we're seeing a strange color shift in the shirt as well. If we look at this on objects, we see a similar effect. And I really like this demonstration. This is actually something we did at a trade show. Again, we're just illuminating these objects with actually an HDR still that's being emitted from these LED panels. And as I've been going through these clips, I've actually been demonstrating to you a very unique capability of the Brompton system, which is actually to produce exactly the same colors, but with completely different spectral quality. So I'm going to flip between a couple of images. This is the RGBW Illumination, so we've got that really nice quality to it. When I go to RGB, you will see the color rendering change radically. But what's kind of unique about this is that if you look at the white chips as I switch between the two, if I can get it to work, sorry, you'll see that they aren't changing at all. So our illumination quality in terms of white is completely consistent. But if you look over on the right-hand side of the oranges, you'll see they're changing color almost completely. Under RGB illumination, which is this, the oranges kind of melt into their red bag. You can't really see orange tones at all. And our reds are really hyped. They're out of balance with the other primaries. But under RGBW light, suddenly our oranges are the correct color. Our color rendering's been massively improved, and all of our tones sit back together. If we look at this on a color checker chart, that I'm sure a lot of people are very familiar with from color workflows, we can kind of see this effect personified. So here we've got the same color checker under these different illuminations, and we can see our red tone. Under RGB illumination, the saturate is really, really oversaturated compared to the other primaries. But under RGBW illumination, it looks much better. Similarly, we can see our skin tones shifting, and we can see that very strange effect on orange. The oranges are very saturated and very red. So what's actually going on here? I showed you some spectra earlier. Well, these are the real spectra of this panel that we've developed. So in direct view, we get these spiky spectra, and by adding this fourth emitter, we can make a much broader, more continuous spectrum, and that's what's giving us our better color rendering. We've actually got light at all these different wavelengths. We've chosen in our solution to support 4 emitters. There are other products on the market that are going for more, but in LED panels, 4 emitters is a very good choice. It's a very good trade-off between the massively increased complexity of the drive system and the results, and there's lots of research backing this up. Using a white LED to make pale colors is actually also much more efficient in terms of power. We're seeing between a 10 and 20% power saving for certain colors. And the screens get less hot. They have better viewing angle characteristics and better linearity characteristics as well. So there are a lot of benefits. Now, we're a processing manufacturer, so to do this, we need panels to work with. And the first RGBW panel on the market is something we've developed with Row, the Row Carbon 5 RGBW, available to order now. And what Row have chosen for that is actually a warm white LED. And this gives a really good performance across a wide range of color temperatures. If we look at our spectra, again, we can see that this is trying to produce white at D65, 6500 Kelvin. And we actually need quite a lot of blue in that spectrum to get that cool color. And you can see on this diagram on the right-hand side, there's a kind of gray line as opposed to the black. And that's actually the spectra of the white LED on its own. And you can see what we're doing is we're adding a lot of blue in there to get 6500 Kelvin. Now, it might be tempting to choose a very cool white LED. You will be a bit more efficiency because you won't have to use your blue LED. But that's actually probably a mistake because we can easily add in blue. We have a blue LED, but once that blue spike's there, we can't take it away. Developing these panels is actually pretty challenging. There are going to be a lot of problems in terms of trying to actually source these LED packages. We need that extra emitter, and the industry as a whole is not particularly set up to make these panels. So this is what we've developed with Rowe, but we will be seeing lots more panels come to the market from all the different manufacturers. To start with, we'll probably see mostly quite coarse panels that are really good for ceilings. They're useful for lighting trucks and things like that. But our vision is that complete volumes can move to this technology, and we're able to drive that. The other unique part of the Brompton implementation of this is color accuracy. And having an actually color accurate output is by far the best workflow. So when we've been setting up these systems to test this and demo it, what we found is that if you get an LED screen backdrop and you get some of these panels that are properly calibrated with this extra emitter, and the output is color accurate, then it gives you a much quicker time to having a plausible looking scene. You immediately get light with the correct color, precisely the correct color, but also with this nice quality. The objects in the scene immediately sit back. They always blend with the backdrop, and that gets you much closer to your desired final result with a lot less tweaking, enable you to be much more creative. We're able to do this because Brompton has developed the Hydra system, which drives our calibration, and the Hydra system shipped from the factory, able to handle these fourth emitters, and that's completely unique in the market. This builds on top of our dynamic calibration technology, which gives you a lot of flexibility to set up the screen how you want, to pick a color space, to trade off various different characteristics of the screen. But rather than other systems where that's all fixed at the factory, you get this complete dynamic capability with Brompton. And we also build on top of that the rest of the feature set that we've just spent a long time developing, in particular Pure Tone, which enables us to linearize the output of the panel, giving you much more accurate EOTF results, so getting the right colors, the right brightnesses, and also things like ThermCal that we can use to compensate for thermal effects on the panel. Building on this dynamic nature, we're able to offer much more control and feedback. And I just want to highlight just one control that we've got here, which is what we call Spectral Preference. So in the Brompton system, you can tell us what you'd like the screen to do. So if your Spectral Preference is set to narrow, 0%, we don't use your fourth emitter at all. If it's set to 100%, we use as much as we possibly can, giving you that massively improved color rendering. It gives us a flexible solution for tuning for the use case in the environment. But it is very computationally complex, and that's why we've needed to use the G1 platform to build this on top of. All that extra power is giving us the ability to make these trade-offs in real time. I should note that I've been talking about RGBW, but we have a little joke at Brompton that W stands for whatever. So actually, we can cope with any fourth emitter, and the calibration system deals with the differing performance. So we can deal with these warm whites we've got in these panels. We can also deal with cool whites. We can actually also deal with emitters that are outside the gamut. When we're building this, as with all the Brompton features that we now develop, we're putting behind it a full API integration. So this can be controlled from third-party control systems, from lighting desks, again, giving that power to DPs and gaffers to actually fully control this. And we've also built in this spectral preview, which really shows you what's going on, the difference between these spectra. And it's pretty remarkable the way the energy gets redistributed. With this emitter, again, we're trying to produce a fairly cool white for this color sample. We can see that under RGB, we have a very strong red spike. But when we start using our white LED, we don't actually need to use the red at all. It's completely off, giving us this wonderful color rendering. Now, I'm an engineer, so I can't leave you without some graphs and some data. So this is the real data from the Rowe RGBW panel that we've got. There's one outside. If you've got your spectrometer with you and you want to measure it, feel free. And we can kind of see exactly what we've been talking about. So the spectra is much less spiky. We filled in those oranges and yellow hues. In the middle, we've got some CRI measurements. And it's quite small, but the way CRI works is it kind of gives you a score for all the different colors. And for red, we get a score of -80. So it's almost, and the worst possible score is -100 under RGB illumination. So our accuracy of illuminating red objects is incredibly poor. It's absolutely terrible. And when we introduce this broadband emitter, that situation improves massively. And finally, on the right, we've got some measurements of TM30, which is quite an interesting modern way of trying to measure color rendering. And our fidelity scores going from 60 to 82. So TM30 also gives us a really nice sort of visual representation. So you can kind of see on the left, there are two circles. A perfect light source, the two circles will be perfectly on top of each other. So the red circle will sit perfectly on top of the black. So what we can see is under our RGB illumination, our greens, our cyans, and our reds are being shifted around. And when we introduce our fourth emitter and we smooth out the spectrum, we get much closer to that perfect circle. So finally, I'm just going to talk a little about the applications for this. And we started from virtual production, and that is the obvious place. And that's what's driven this technology to be able to be developed. This isn't really that new, right? Lights have been doing this for a long time. Ever since people realized they could make a light for domestic use or for theater with LEDs, they ran into this problem. But it's quite different to do that in a video system. Video systems need to respect very precise input colorimetry, that single right answer that I was telling you about before. And we also have to do this for a large number of pixels, potentially millions of pixels at quite high frame rates, much higher than is generally deployed in lighting. So we've needed virtual production and XR to really help this technology come to market, to give us the impetus to develop it. But now we have it, there are a lot wider usages of it. So basically anything where an LED panel illuminates someone is a candidate, or an object is a candidate for this technology. So fashion and retail, designers pick colors very carefully, and they want those colors to be faithfully reproduced. You could imagine even in a store where you're, say, selling shoes and you've got some LED screen behind them, the light from that LED screen is going to be illuminating those products, and it's going to be giving them these wild color shifts. They're not going to look correct. We've also actually had a lot of interest in this technology in live events. If you've got a massive stage and you've got quite bright content, all your costumes and all your set pieces are going to look the wrong color. So that's really interesting. Again, virtual production drove us to develop this technology, but it has much wider applications. And finally, it's a buzzword, but imagine the metaverse conference room of the future where a whole wall is an LED screen. That would be a fantastic experience, communicating with your colleagues across the world, looking at them like you're looking through a giant window onto their conference room. But imagine how awful that's going to be if everyone looks really red. I like to say your execs will look like lobsters now. And that's not going to be a great experience. So actually, having this good quality light, this correct color rendering, has a very wide range of applications. As I said, we've got the panel outside. Please do come and see it. It's a fascinating technology, and I think it's going to change the game in virtual production as well as in these other areas. That's all from me, but happy to answer any questions. Thank you for listening.